Now let's face it, none of you are ever going to build this. Wise words from a wise man, a teacher that I've studied under for many years. However, I'm a stubborn asshole and I don't listen. So I'm going to build the Stuart Progress. This is an engine made of cast iron that I got from Britain last year. This project vindicates my friend Al, who drove 8 hours to get me these castings. They're mostly cast iron with a few brass bits here and there. This is the Boxbed, the base that the engine sits on. A nice little STP-1 cast under there. I've already taken the liberty of painting and marking all of these. This is the cylinder casting. This is the lower head where the piston rod passes through. This is the cylinder head that sits on top. This is the crank disc. This is the body, which obviously defies being held because it's a very tricky shape. This is the flywheel. It's very heavy. All of the fasteners, the graphite yarn, and a spring for the pivot are all included in this little plastic box that came with the engine. I also get a few pieces of bar stock, 1/8 inch and 3/16 inch. This is cylinder lighting, meant to hold in some insulation to keep the heat in. This is the brass steam gland. It looks kind of ugly, but I think I can fix it. This is the piston. And this is the big end, little brass square stock that I'm going to have to turn down. You also get a large piece of gasket paper, very clearly British. It even says so on the paper. There's no plans per se on this engine. You get a book that comes with it, but it kind of hand waves about the dimensions except for the most important ones. So you get a lot of freedom in how you machine this thing, which is good because I'm not a very good machinist. I'm just a guy who bought a lathe, remember? Recently, I've also bought a mill. I can hear the comments typing furiously on my choice of vise, but it holds my work securely. I also use this dead blow hammer to make sure that my work is secure in the vise. Some people are typing that I'm not doing it right, but I find an empirical approach is best. I'm new to using a mill, so shaving this surface flat will be my first operation. Flatten these two pads so the engine can sit upright. In this video, I will be machining the box bed and frame, allowing me to build the engine upward and outward. This is a technique used by Quinn at Blondie Hacks, who has taught me most of my machine shop skills. My choice of cutter here is a 3/8 inch carbide end mill with 4 flutes. I'm cutting at a 20 thousandths depth of cut, and it mows through the cast iron with very little difficulty. The operation here doesn't have any dimensions. I essentially need to flatten these two pads so the engine frame can sit on top of them. When I cut them, the surface finish was kind of bumpy, so I went back with a faster bit speed and a very small depth of cut, say 3 to 5 thousandths, and it gave a much better surface finish, flat and smooth for the engine frame to sit on without any wobbling or rocking. Once they've been machined, I'm using the calipers to measure the height of the pads. It's not the most accurate tool, but if you know how to use it, you can get pretty good results. According to these, I have 36 thousandths, which is slightly more than 1/32 of an inch. These little bosses on the side, which I'm milling flat now, will serve to allow me to clamp this down to a piece of wood or other baseboard. Model engineers usually counterbore or at least flatten areas where nuts and bolts will clamp down on metal surfaces. That way you're not clamping on an uneven casting. Once I'm done flattening them, I'll drill 1/8 inch holes through. To mount this, I have 3 options. I could put machine screws down onto the holes and tighten them on the bottom. I could also make threaded studs and tighten them on both sides with nuts and washers. Or I could fake the look of studs by putting a machine screw up through the bottom and tightening a nut and washer on the top. Another trick I learned from Blondie Hacks. I'm using a round rod, in this case a transfer punch, to find the center of this cast boss. I line up the round edge of the rod with the cast feature, and it helps me find the center a lot easier than by using the DRO to measure on a uneven cast surface that I can't necessarily trust. I mark the center of the hole with a center drill. Then I go back in with a 1/16 bit and drill the hole through. You see me here buzzing the outside of the casting. Oops. I can paint over that later. I'm not going to ream these holes. They're just getting drilled with a 1/8 inch bit. They're going to pass a 440 screw. I'm moving to the other side so I can mark and drill the other mounting hole. I'm going to use a transfer punch in the same way I did before to locate the center of the casting. I used the transfer punch that was closest to the outer diameter of the boss. Go in with a center drill to mark the hole. Go in with a 1/16 bit to drill through. Since it's a small hole drilled deep, I go in and out several times to pull chips out of the hole. Then we go in with a 1/8 inch bit to open up the final diameter. Again, I'm pulling in and out to clear the chips out of the hole. These are the milled pads before I went back and flattened them with a finishing cut. They were a little rough. Next step is going to be milling off the bottom to flatten it. I put the box bed in my vise for milling. This was difficult because the sides aren't straight and it wanted to pop out. I also was very careful not to apply too much pressure because cast iron will flex a very little bit before it cracks, but not much at all. So I didn't want to break this expensive casting and have to go to England for another one. I don't have dimensions for this cut, so I'm only taking off what I need to flatten the surface on the bottom. The blue marker is a good indicator for where I still need to cut. Once I'm done, I will put it on my bandsaw table, which is flat and cast iron, and test it to see how flat it is. Although I'm striving for perfection here, if I don't get that, it'll be bolted down to a piece of wood, so I can shim it if absolutely necessary. With that, we are flat. The engine frame is a difficult piece to hold in the vise. Everywhere you want to put a vise jaw, there's something in the way. I've marked in blue the surfaces that will be machined. I'm going to flatten all of those, starting with the bottom. The bottom will be my reference surface, and then I will flatten the top and sides. This side here will be used to drill the steam passages, although I'm going to route one of the channels up through the top and plug the end. When I put it in the vise, I'll be using a parallel to make sure that the bottom face is lined up with the top of the flange on the bottom. That way the foot is not thicker on one side than it is on the other. This is my machinist hammer. I'll be using it to tap the parts in place. Some people complain about how I designed it. I've ignored all their comments. I make it how I like it. When I need a new one, I'll make a new one. Here, you see me using a parallel to line up the top face of the foot with the top of the vise jaw and clamp down the vise on the port face. This will establish some kind of reference. Then I use my hammer to beat it like it owes me money. Now I'm using the same 3/8 inch cutter to flatten the base, cutting off the flashing and then the scale to make it a flat surface. When I finish, the surface is going to be somewhat rough, so I'll take a light finishing pass at a higher speed, which will make it mirror smooth. I make my cuts in a counterclockwise direction to make sure that the rotation of my cutter is always conventional milling and not climb milling. I don't want to climb mill until the finishing pass. Sometimes I do the finishing pass in a counterclockwise spiral and sometimes I do it in a clockwise spiral. I find that the direction doesn't matter. As the cut is so light and the speed is so fast, it still takes off a minimal amount and leaves a good surface finish. Now you'll see me taking the finishing pass by going back and forth in rows rather than in a spiral. I'm trying out different techniques because I'm still new to this milling thing. Normally when you're milling you don't go back and forth in a zigzag pattern. However, I'm taking such a light cut that it shouldn't affect anything. I'm going to pop the frame out of the vise and show you what it looks like. You're going to see a lot of tool marks on the bottom of the part from the cutter going over it back and forth. But I can tell you the surface is exceptionally smooth. It feels like glass. It's almost like Joe Camel should be advertising it to little kids. Damn cigarette companies. And it sits flat on the mill table. Next will be to flatten the top of the frame. I'll be drilling one of the seam channels through this once I have the passages drilled from the end. Because the machine bottom of the frame is sitting on the parallels, this surface should be parallel to that surface, making further machining easier. The steam port that sits on this face will be the exhaust port, while the input will be on the right side facing horizontally. The advantage to this is that gravity will feed any of the oil droplets that come out of the exhaust back down into the port, which will come back down into the engine to lubricate it. You won't get that if the exhaust is on the right side. The steam droplets will simply get fed along the line until they come into some sort of steam separator. If I want to make the surface finish of these better, I'll flatten them using a piece of plate glass and some sandpaper. However, the top surface there will be painted, so I don't need to worry about it. This begins the most critical operation on the engine frame. I'm marking the center of the axle shaft so I can drill the bore for the axle. Then I will be drilling the pivot pin hole and then machining flat the port face. It's very important that the axle shaft and the pivot pin are parallel to each other and that the port face surface is 90 degrees from these. If the cylinder doesn't sit flat on the port face, then it will leak steam and oil everywhere. I can't have that. One technique I've seen for correcting for an imperfect alignment is to clamp the cylinder onto the port face after machining. Then, with a few drops of Loctite, insert the pivot pin and let it dry. That will permanently install the pivot pin in the cylinder and also make sure it's aligned with a 90-degree angle to the port face. That way when it rocks, it doesn't leak. I'm center drilling the crank axle bore and then I'll move over to drill the hole for the pivot. Something I should be doing but I'm not is putting a machinist jack under the right side where the crank axle will be drilled. That way the pressure of drilling through that long bit of cast iron won't cause the casting to rock as I'm drilling through. One thing you'll see here is multiple drilling operations in the same position. Because it was difficult to get through this bit of cast iron, I wasn't able to drill deep enough to get through with the first or second drill bit. I had to use the third drill to get all the way through. Here I started with a 3/32 inch drill bit. Then I changed up to a 1/8 inch. I'm making multiple plunges to clear chips. When you have a long skinny hole like this, the drill bit tends to jam up and you need to remove the chips frequently. Lastly, I'm coming in with a drill bit that's one size under 3/16 of an inch. It's something like 11/64. You see me here using WD-40 to lubricate the drill. Normally I wouldn't use lubricant with cast iron, however the casting wasn't cooperating and I wanted the hole drilled. Once I'm done drilling, I come in with a reamer. A reamer is like a drill bit, but its focus is not removing metal, but shaping the hole. Holes cut by reamers are much rounder than drill bit holes. They also are ground to a precise dimension, so they cut much more accurately than a drill bit will. The hole I cut with a reamer can be counted on to be extremely close to 3/16 in diameter. People with more money than me buy over and under reamer sizes. In addition to the standard dimensions, you have reamers that are 1/1000th larger and 1/1000th smaller. There's one cardinal rule about reamers that every YouTube machinist will tell you. You never run them backwards. If you do, it will ruin the flutes. These cost so much, you definitely don't want that. With the crank axle hole completed, I'm going to move back over and finish the pivot hole. Already drilled a through hole. I'm going to drill one size under 1/8 inch and ream 1/8 inch for the pin that came with the kit. In using WD-40 here, I found the one way to make cast iron messier, something that most people didn't believe was possible. Cast iron is seriously dirty stuff. Now to flatten the port face. Because I'm doing this operation in the same setup as the pivot bearing was drilled, they should be extremely close to 90 degrees. I'm using this copper wire to ensure that all pressure from the movable jaw is placed on a single point on the top of the casting. That way the machined base sits flat up against the fixed jaw. I'm machining in a counterclockwise spiral pattern per my normal operations. No matter how good I get the surface finish, I'll still need to polish it using a very flat surface and some abrasive powder or sandpaper. It's a bearing surface with the back of the cylinder, so the less abnormalities I have in the surface, the less wear there'll be on both sides. I'm taking a measurement now to see how proud the port face is off the cast surface below. It looks like 66 thousandths. I'll take a finishing pass and I'll also polish this surface at the end. When I take a finishing cut, I speed up my cutter considerably. I don't have a digital readout on my mill like I do my lathe, so I never know exactly how fast it's spinning, but I use tick marks on the dial of the speed control to get close. They're a pretty good point of reference. Maybe someday, when my performance expectations are higher and I have a little more skill, I'll buy a tachometer for my lathe so I have a digital readout. For now, I'm still mastering the basics. Well, that's too bad. The bearing holes were not drilled center on the cast bosses. So, what am I to do? Do I need to go buy a new casting from England and start over? I don't think so. For the axle bearing, I'll simply turn the outer casting to be concentric with the bore inside. I'll do this by chucking it up in the four-jaw chuck, putting a dead center in the axle hole, see the machine surface there, and using a dial indicator to adjust it in until there's zero runout. That way the axle hole is concentric on the axis of the lathe. Then I'll turn the outside of the casting to match. As an aside, I drilled and tapped those two mounting holes off screen as practice for learning how to use my DRO. To dial this in, I'm putting this dead center into the hole, rotating it around and seeing how much it deflects, and using a dial indicator to reduce that deflection to zero. It takes a little while to do, but it is a pretty good technique for getting things centered on the lathe. Here I'll show the mounting holes as drilled in the box bed. I've got 632 machine screws to secure the frame to the bed. The first step in this operation is to make a facing cut across the barrel. Next, we'll take successive cuts to reduce the diameter of the barrel, true it up, and clean up the cast surface. Cast iron is tricky to turn on small machines because the outer surface of the casting tends to form a hardened scale. Your inclination will be to take deep cuts and cut through it all in one go. However, small machines like this aren't always up to the challenge of cutting through all of that in one, and you get chatter and vibration, which tends to leave a poor surface finish. So the answer is to be careful, take your time, and take small cuts until the outer surface of the barrel is cleaned up and concentric with the bore. I'm taking a finishing cut at a higher speed. This is kind of risky as the higher speed causes vibration with such an off-center mass like this casting. The key is to be careful and also don't stand anywhere the casting can hit you if it flies out of the machine, which is pretty much anywhere near the machine, so I'm not safe no matter what I do. Now I'm switching to a 90-degree chamfer tool so I can deburr the outer and inside edges of this barrel. I could deburr it by hand, but doing it in the machine is so much simpler and takes a lot less time. I could also do it with a file, but putting a file in the middle of the spinning mass like that is a surefire way to get hit. I don't feel like getting hit. We have what looks like some slight chatter marks and some ringing from when I didn't withdraw the tool back to the right place every single time. It'll add a little bit of charm to the engine. Taking a measurement here in case I want to duplicate it on the other side. And the verdict is slightly less than 306 thousandths. Before I turn this end of the bearing down, I trimmed it to 1/4 inch using a hacksaw. To clear all the angles and shapes on the casting, I'm having to use a boring bar turned upside down. When I stopped turning this side, it was a bit larger than the other side, which measured at 306 thousandths, but I decided it was acceptable, as this side's going to handle more of the forces from the crank being pushed on by the cylinder. This concludes the first stage in this engine project. My next step will be machining the top end, that is the cylinder, the pivot, and the heads. Once I'm done with the rest of the engine, I'm going to revisit the frame so I can drill the steam passages, the ports, the plumbing, and a lubricator for the crank axle. Thank you for watching this video, and I'll see you next time.